Okay, so this is, like I said, just a really rich task that I actually did in real life. Um, so that, and I actually messed it up. I made such a big mistake, but it's okay. And I'm going to talk about that mistake itself. So stairs are one of our most common applications of Trig. And I actually have a little document that hopefully I'll get the chance to show you so that you can see a little bit more application of the Trig.
Okay.
So my father presented this problem to me. He needed to build stairs from the second floor of a balcony of his shop down to the ground. And his question for me is, what size of board do I need to buy? And I was like more than happy to help him solve this problem. Um, and so I presented this to my students and I asked them what I needed to know to solve the problem. And they said, well, we already know Pythagorean theorem, so we're going to do Pythagorean theorem. And I was like, great. So then I showed this picture or these pictures. So this is the actual balcony up here, and these are the stairs. And at the time, we only had these support posts up, and we only had, I forget what this balcony frame is called. There's a specific one when it goes against the house, possibly a header, but footer. It's a footer. That's what it's called.
Probably something like that, yeah.
Yeah. So we had that footer there and just the post. So none of this was here. And my dad wanted help calculating all the materials for the building. So this is kind of this, we're getting a little bit of that application to the next section. This one here, up here, would be like an isometric drawing, so you can see it in 3D. And this would be where we're getting into some of the orthographic drawings, where I'm looking at it from the front and I'm looking at it from kind of the side, back type deal. So that's something that we'll go into later this afternoon on the different views of drawings.
Okay.
But essentially, we had this post back here and this post here, and we had the footer along the wall, and that's all that was there.
That's not a lot to support.
Yeah. And so and he just kind of drew me a little picture and he said, this is what I'm thinking. And what I needed to tell him was the length of this stair runner coming down the side here. So that's this big, 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 big board here. And I'm going to point it out a little bit later, but I actually really messed it up. So there's this extra stair here.
I saw that. I'm like, wait a second.
Yeah, so me, the math teacher, made a mistake. And one of the beautiful things about math and the math brain is that it doesn't exist. So we're going to talk a little bit more about that, but I've done a lot of kind of reading and just lots of extra information and professional development on brain science, particularly surrounding math, but surrounding pretty much anything else. And one of the big things that they have found probably in the last 5 to 7 years is that mistakes actually grow your brain. So me making this mistake actually made me understand the trig concepts better than I did before I even started this problem. And that's honestly, they did it through brain science. They hooked up people's brains and they compared people's brains who got the question correct right away versus someone who made a mistake and then later tried the problem again. And it didn't matter if they got the problem correct or wrong the second time. What mattered is that their brain lit up more than the person who got the question correct.
So it was firing more.
It was firing more. Yeah. So they were making more connections. They were actually thinking better when they had made a mistake. So at first I was a little embarrassed to show this problem, but then I did a little more brain science and was like, oh, wow, this problem actually made me smarter. So
well, it deepened your pathways in your math part of your brain?
Yes, yes, it totally did. And so it just kind of blew my mind that me making such a big mistake actually made me smarter, and I just wanted to share that with everyone.
Well, it's not that bad of a mistake though. Like, yeah,
Well,
all
it
you
is
need
when
is
you
a
get to stare
saw.
at it all the time. It's one of those things when you get into adulthood and you're like, "Oh, I made that mistake," and you stare at it every day. But
Oh, it doesn't look that bad though. You could just put up a fence post at the end of it, or like two posts at the end with lights on it, and it would
oh,
probably cover up most of it.
oh, there we are solving our design problem. That's also one of the curriculum goals for this course. Okay, so this is the information that he gives me, and I found a little bit more information on this as well. That if we're not too overwhelmed at the end of this, I'll be able to kind of show you that info too. But he essentially shared with me that for stairs to be safe, they need to be between roughly like 6.5 and 7.5 inches high. If they're any lower than that or any higher than that, they actually cause a tripping hazard, statistically proven and mathematically supported that if your stairs are too shallow,
Then your perception from your eyes won't get the right, like, it
yeah,
won't add up in your brain, and then you'll trip on it with your foot because you don't see
yeah,
it.
because our brains are conditioned to 7 inches. Like they are conditioned to step at 7 inches. And I find that funny that we're all conditioned to do that, but apparently it's the ideal foot raise. So if your step is too short, then what happens is you raise your foot to the 7 inches and then you fall until you hit the stair, which can cause an accident. But then also, if the stairs are too steep, same thing, you raise your foot and then trip because you don't have enough clearance. Or the same thing going down, your foot expects to hit a stair at 7 inches. And if it hits a ground before that or after that, it can cause another tripping hazard. So I thought that was really cool to find out.
Yeah, that is interesting, especially that it's seven, because that's like the number everyone says when you say pick a random number between 1 and 10. It's usually like around seven, or it is seven.
We're drawn to it apparently as a species.
Yeah.
Okay, so then he told me, then we went out and we did this measurement, and the balcony is 8.5 feet up. And then he told me that he has boards, and just to make life easier, let's see if I can get a piece of it. Yeah, so he had these boards here, and he's like, just to make life easier, I don't want to have to cut these boards down because trimming a board along this long edge is not as easy to do.
It's
Um,
annoying.
yeah, you have to have a bigger saw. There's more potential for danger, and it's just not as easy. So he wanted to keep the board widths the same. So he said, I bought these boards. They're 9.5 inches. So I just want to keep that. Like, I want the stair to be 9.5 inches wide. And I was like, perfect, no problem. So then he says to me, what size board do I need to buy? And again, that's the stair stringer that the stair's attached to on the sides here.
Oh, along like not the actual stepping ones, the ones that hold it in place almost.
Yes, the ones that hold it in place.
Oh,
So So this is some information, and I think I knew that I was making a mistake in my thinking because I spent so much time on this problem and I solved it and I used a calculator, and then I didn't trust the calculator for some reason. I started doing it by hand because there was just something that was stuck. It just wasn't working out for me. And this is the thing that caused me the most trouble, is that the balcony is 8.5 feet up. So we calculated it, and I did it perfectly in this world. But the trouble is where we measured this height of the balcony,
that looks
and
way higher than 8 feet.
well, it's 8.5. And silly us, we did it from here down to the ground.
Oh, so that's 0.5 off, or that's about a good foot, isn't it?
Well, it's actually quite a bit more than that. This picture is a little bit deceiving, I think, from the way it was taken. But so we measured from here down to the ground as the 8.5. And what we should have done is measure from out here down to the ground. Because if I show you,
Basketball player from the NBA could literally like have their head up there almost. Like that's crazy. Because isn't there like some 7 foot tall basketball players?
yeah, yeah.
So they could literally like have their head touching the top of that.
Yes,
That's
exactly.
ridiculous.
So this may help, but one of the other things that we had forgotten about is grading. So every building is set higher and then the ground slopes away from it. So there's another mathematical term, slope. We use that. And slope can also be called grading. So if you've ever done any landscaping, they talk about the grading. And essentially it is they want the land to get lower around the building so any water moves away from the building rather than towards the building. So silly us, we measured this piece here. And we should have actually measured here because if the stairs had been against the building, then they would have been long enough. Like this never would have happened. They would have been way over here and where the ground is higher.
Yeah, that'll happen often.
Yeah,
but that tree stump is in the way, and that would have costed like an extra, like what, $300 or $400 extra bucks.
Oh, this is just like a movable stump.
Oh, okay.
Yeah. It's just my stepmother uses kind of natural seating, so she has a whole bunch of these around as footstools and seats and stuff like that. So it's pretty cool.
We used to have those, but they rotted away because our tree was rotten. It was like way taller than the house. It was like probably one of the tallest trees in town. And it went in the field and we had to chop it all up because it was rotten. We didn't want it to fall on the house.
Yeah, well, that's good natural sustainability there. Makes good soil. Okay, so this was the problem. So this is why I actually made a mistake because we measured against the house or against the shop instead of measuring the height where the pole would be. So we didn't account for this grading. And I'm going to talk about the grading a little bit later when we try to apply some trig to it.
Well, you have to calculate the slope, I think.
Yeah, we do have to calculate the slope. And if you recall, I'm going to just write on here just because you mentioned it. That was lovely. Thank you. Nice segue into that. Come on, there we go. So slope they call the rise over the run, if you remember that. So it can be calculated using, let's say another triangle. We're just going to do a green one here.
Pi r squared? No, I don't think it'll be calculated by pi, can it?
No, pi is for circles. So this slope can be calculated
by doing triangles?
Yep.
Oh,
That's and that's one of the things that I always find so challenging teaching math because I know more math, I can see how it's all interconnected. Whereas like people coming in grade 9, even by the time you leave high school, you're just not seeing how things are interconnected and they seem like totally arbitrary concepts that aren't even related. But these things are all intertwined and we're giving you like kind of really simple examples to get you started. Whereas if we were able to show you what they're used for, like a lot more in the world, then you might be able to make more connections. So this is the whole reason why we do trig. We do trig for stairs, and we do trig for the sloping of the land.
Well, you use trig for almost anything when you think about it.
Yeah, we use trig in manufacturing because they have wedge slotting to hold pieces in manufacturing. They use trig to bore the holes in your rims for your tires.
Oh, I thought we were talking about boreholes, and I'm like, when did we get to mining?
Well, see, that's the thing is like there's math everywhere, but we just don't. I guess we get distracted by all the hand calculations, the manual calculations. So, yeah, so this slope applies here because slope talks about the rise, which is this piece here, over the run. And that is actually going to give us grading. That's another term that's used in building. It's used in landscaping because we're talking about how the land slopes away from a building.
Yeah, and you want your house to be level, so you need to level out that part, but slope it down so that the rain doesn't collect in your basement.
Exactly. That's exactly what grading is for. So I can show you what we would have done in this case. So for me to try to figure out what the slope or the grading is, because it was actually significant, I kind of needed some measurements.
That's like a 45-degree angle almost.
This one here?
Yeah, isn't that?
Well, actually, 45 is a special triangle. It let's see if I can do that. That 45 would look like this.
Oh, okay. So a bit smaller than 45 then.
Yeah. So that 45 would look like that. Where's my? There we go. It's been a while since I've used Smart Notebook, so no, it's not going to like me do that. Select and delete.
Oh, smart boards are almost gone.
Well, I like the whiteboard aspect of it, so we're still using that.
Oh yeah, I just think they need to update them.
Yeah. Okay. So I needed some information. So we actually went out and we measured this part here along the house. So I'm just going to make a duplicate of this one, so we can so I can show you how we did some of the calculations, because this is also a mathematical application. So we took this measurement here in red, and that one was, I just want to make my line. Yeah, the line's a little bit smaller. This one was 8.5 feet. Come on. Now move my picture. The problems we have with tech. All right, here we go. So from the bottom of the balcony down along the house, this was 8.5 feet. But feet aren't as easy to work with when we're doing some of these calculations. So my previous class said, well, let's convert that to inches because it's easier to work with kind of the solid number than it is to work with decimals. And so that's something that we could do, but I don't necessarily think that we have to do it.
Yeah, I mean, there are many ways you could go about doing this. You could even get like what are those called? Like a giant 2x4, put it on the edge of, or yeah, kind of rest it up against that, find out how tall it is, and then get the same board and screw it onto the top of one, and then just kind of like have a giant L, and then screw another one on down, and see what you need to add on to the bottom one.
Mm-hmm.
But, I mean, be a little bit more work. It's just if you don't want to do the math.
Yeah, so there's a couple things that we can do. So there's actually a tool that you can put on the ground, and it sends a laser. So you set it upright and then you angle the laser to go where you want, and it will tell you what this is called, the angle of elevation, also a term that we're going to use in this course. So there's a tool that can do that for you.
Okay.
But if we wanted to figure it out, we could do a little bit different math. So what we actually needed to do is we needed this measurement, but we also needed this tall measurement here. And so my dad and I went out and we did our best. It was crazy. We like propped a board up against this post back here, and then we put a level on it, and then we held it and measured down to the ground because we didn't have this balcony here. We had to kind of make a guess afterwards that.
Oh, did you guys build it all yourself?
Yep.
That's really impressive because like you needed to get all the posts down before you could even start getting the deck up top done, and building up that high is kind of sketchy.
Yeah. Yeah. I also helped him build the shop too. So it was an interesting experience that we had for sure. So from here down to here, this measurement was, sorry, I had it here. I just need to find it. This one is like 11 feet. Is that right?
11 feet? Doesn't seem right, because that seems really tall.
It is. It is. The grading is actually quite intense. This picture is taken from higher up. So we're actually looking down on it. So the grading doesn't seem as hard, like as harsh. But if I had come at it more level, you would have seen that it actually slopes down quite intense.
Well, you probably took it with your phone too, right?
Yeah, sorry, that wasn't 11. It was, yeah, 10.25.
Because phones don't have a lot of depth in their cameras.
No. So there, it is a little bit deceiving. So we actually were supposed to have this height, and we used this height. So if we wanted to use Trig to figure out the grading, then I would also need another measurement as well. So I would actually also need to know the distance out, which I'm doing it in the green, so you'll see that it matches up with this bottom part here. So if I want to know the run, we measured out to the post from the top of the footer here all the way across to the post to figure out how far that was across, and that one was that one was 6 feet ish, give or take. It was a little bit more, but we're just going to keep nice, easy numbers here. So the run in this case was 6 feet, right? And we needed to figure out what the rise was. So this is how the difference between where the bottom of the shop is and where the bottom of the stairs would be. And so that we just need to take the difference here. So my tallest measurement is 10.25, and I'd subtract my 8.5 from it. So it's actually almost 2 feet difference.
That's actually quite a lot, I think.
It's a lot. It is. It's very deceiving in this picture, but it actually is that height. So these are the two measurements that we have. And so if I wanted to find out the grading of this angle here, the grading would tell me the degrees of that angle. And so this is where we get into an application of the trig that we're learning.
Okay.
So one of the go so you can see the picture. So one of the things that we use, there's 3 formulas that are used for right triangles, and this is a right triangle. This is a 90-degree angle here. I'm sorry, my drawings are not that great. I'm actually not artistic. I can't even blame it on the tech. I'm really not that good.
Better than I was doing on mine.
So we have this lovely acronym that helps us remember what the formulas are. And we don't actually have to memorize that. That is not something that I expect anyone to do in this course, is memorize formulas.
I remember this.
Yeah. Perfect. So in this case, S is sine, and it's equal to the opposite over the hypotenuse, and that's where the OH comes from. And cosine is equal to the adjacent over the hypotenuse, and tan is equal to the opposite over the adjacent.
My teacher last time I did math split them up. So she would do SOH and CAH and TOA and kind of write it at the top of my page, whichever one I needed to be using to help me go through it. That's all I remember though.
Yeah, so we're just gonna work on that for now. And so essentially one of the things that we need to do first, before we can even like pick a formula, we need to know what we're dealing with. So I'm just going to, maybe I'll stick with the green. I'm just gonna redraw this triangle so it's nice and pretty-ish. It's not exactly to scale. What happened there? Again, I'm not the best at drawing, but I'll try my best. So it looked something-ish like this. And one of the first things we need to do is actually label the triangle. And how to label is you actually have to get the angle first. So I need to know, I need to sit on the angle in order to view. And it's all about perspective. So like we just talked about perspective in this photo, it's very deceiving because of the angle that I'm looking at. And trig is very much the same too. We need to get on that angle first. So first thing we need to do is label the triangle. So in this case, I go to the angle, and the opposite side to the angle is all the way across here. And then the hypotenuse is across from the 90 degrees. And the adjacent is touching the angle. So the adjacent is with the 90 and the angle. And we don't use as much English as our predecessors used. And adjacent actually means beside. Like if I asked who was adjacent to me, they would look to beside me and tell me. We just don't use that word. It's not actually a math word. It's actually an English word that we just don't use very often.
That makes a lot more sense.
So the first thing we want to do is label.
Wouldn't it be ka? So like soka toa, so it'd be the ka.
Well, let's look at that. So what do I need to do? I need to extend my page so we can have a look. Okay, so I've labeled the triangle, but now I'm going to put in the measurements, because that's what's also going to help me. So this bottom is 6, not 6 inches. Seriously, Rose. There we go. I'm trying. Using tech is not the easiest all the time. I'm pressing the button. There we go.
Is your laptop a touchscreen?
Yes. Yeah, I have a life book. I love it so much. It's very helpful.
Heard of a life book. Know where from? Lenovo?
No, it's Fujitsu.
Oh, pretty much the same, I think.
Yeah. Okay, so we've labeled the measurements that we have. So we have 6 along the bottom, which is the run, and we have the rise, which is 1.75. So if we look up to our formula, we need a formula that has adjacent and that has opposite.
Okay. So adjacent and opposite?
Yep.
So TOA would be that.
Okay. So the second step is to, oh, I don't want that color. Pick the formula. Okay, and you said it's TOA because we have the opposite, we have the adjacent.
Yep.
Okay, so then from there, we're actually just going to write the formula. And this is the probably number one mistake everyone makes is they forget to put the angle in. And I come from a background of math, so I actually use Greek letters because I understand that later on when we start using like a squared plus b squared equals c squared, if I put a little a in there, then people get confused. So I actually use theta because it's just easier because you're not going to see it anywhere else. You're not going to get it confused with a length measurement or anything like that.
Hopefully I'll for that. Theta over A, which is something you said before, but I don't remember.
No, so opposite over A.
So adjacent.
Yeah, opposite. I'll do this. Opposite over adjacent. I don't just have as much room to write out the whole thing. So we just need to make sure that we put that angle right there. So the angle always goes with the trig name. So sine theta, cos theta, tan theta. We just want to make sure that we put that there. In some classes, you will see the teacher, they'll put, instead of a theta, they might make it simple and they'll go x, tan of x.
They just make it into a variable.
We just make it into a variable. That's the
If
ultimate.
I see theta, then that's just a variable.
It's just a variable. Yeah.
Okay.
So then we put in what we know. So we don't know tan, and we're trying to find the angle, so we don't know it. But we do know the opposite. The opposite was 1.75.
And you divide that by adjacent or, yeah, I think divide it.
And the adjacent was 6. So that was this piece here. Just going to label my angle there. Okay, so if this is what I have, then this here can get very confusing because a lot of students are terrified of fractions. But a fraction, it just means divide. This line here is called vicundum, and it just means divide. So I don't know this info, so I'm just going to rewrite it. But I can change this out of a fraction. So if I just put 1.75 divided by 6 in my calculator, it's going to give me a number.
Okay.
So it gave me 0.2916, and the 6 goes on forever, so I'm just going to put that in. And the thing about trig that we have to be really forgiving with is that if I used the whole number in my calculator, I would get a different number than if I used this with 5 decimals, or if I used 2 decimals, or if I used 3 decimals, or if I used 1 decimal. I would get a slightly different answer. And so students are always discouraged when they get a different answer than someone. And I have to say, whenever we're doing trig, it's a range of numbers. So as long as you're close, I'm happy. because the whole point is not that it's right on in this case, because the perfect mathematical answer would be using the calculator with no rounding, but that just doesn't work out for most people. So when we do solving or balancing equations, like you and I were talking the other day, if I needed to get theta by itself, then I would need to get rid of the tan.
So then you just plus tan by itself, and then tan is gone.
Well, we're not plus tanning.
Or
There's
negative.
a special kind of button for this, and this is the trouble with math, is it's so intertwined that I haven't taught you exponent laws, so you're not going to quite understand what's happening.
Isn't it squared at the top to get rid of it or something?
No, tan squared is totally something different, but you're giving us lots of good things to talk about. So this is like, if we want to think about it, it's kind of like tan times theta. So if it's multiply, then we actually need to do the opposite and divide by tan.
Right. I remember that. That's what always threw me off. I'm like, never forget
Yeah,
it.
and the whole goal is to cancel these two tans here. So I'm dividing by tan to get theta by itself. So that cancels. And then I'm left with this.
But
and
that can't do anything because tan isn't technically anything.
Right. But exponent laws, which we totally haven't done yet, we're doing tomorrow, but it's kind of like everything is so intertwined, it's hard to decide what to do first. But essentially, whenever something is on the bottom of a fraction, it actually means to bring it up to the top with a negative exponent.
Oh, right. I think I learned this a little while ago.
So it's not this number divided by tan, which is it's technically kind of mathematically like that. But to take the tan out of the bottom, and this will make more sense after we do negative exponents tomorrow. But when something's on the bottom, if I raise it to a negative exponent, I can bring it up to the top. And this is actually a button on the calculator. So you have to have a scientific calculator for this course. And I actually have one on my computer, but it's not as easy to run as you would think. So it might be best if people are used to having their own calculator that they use, like a handheld one that I have in front of me.
They can just use their phone too. Like all they got to do is turn it sideways.
Yeah, and the phone is the option too. The thing is, though, we're going to practice how to use our calculator too, because so this one here, it actually has a trig button, and I'm going to say trig, but I don't see the tan with the negative number, so I have to tell it to do a second button, which is much like if you're on your calculator, you tell it like second function to get to the button above.
That's what I was thinking of earlier when I was doing backup there, when I said, oh, can't you cancel out with the second?
Mm-hmm. Yeah,
I mix everything up. Like there'll be some things that I think, it's all a mess in my brain.
Mm-hmm. So essentially what we're going to do is we're going to take this second function of tan. Oh, I already have it in there. What was I doing? Clear that. Thank you very much. Okay, so I go to trig. I take the second function of tan, and my handheld calculator tells me to do that first. 29167. So take the second function of tan and then input the number. Most phone calculators or computer calculators will actually make you put the number in first. So I have to put in this 0.29167, and then I have to tell it to take the inverse tan.
Okay.
And that's just the difference between calculators. So my handheld one tells me to do second function tan and then the number. But most likely, if you're using your phone calculator or if you're using the computer calculator like I have here, you have to put in the number and then the tan. It's down the line when you're doing math, it's good in some ways and bad in other ways. And it just, as long as we know how to use it on our own device, then we should be pretty good.
Yeah.
Okay, so that tells me that that angle theta is actually 16.3 degrees, which is a pretty huge grading. Like that's actually really big.
No water getting in that basement.
Yeah, so there's no water getting in that basement. So like most gradings for properties are like a 1.5 grading.
And that's like 16.
Yeah, and this is 16. I wish I could take you outside and show you ours, but the grading on the property for my house is, gosh, it's got to be closer to 30 degrees because they accidentally built our house higher than our neighbors. So they had to grade down to our neighbor's house, which is totally perfect because we will definitely never get any water in our basement.
Well, don't you live in a city though?
Yep.
Does the city flood a lot, or?
It depends if you have good sewer system and that type of thing. It really just depends. And it depends on like if your basement's solid, if you have any cracks or something that you can get a little bit more flooding. But they do lots of work to make sure that doesn't happen. City planning, if you're ever interested in geography, take some GIS and that can get you into some city planning.
I can't take geography. I have no interest.
Okay, so that was one way to apply the trig.
That's a little bit of a complicated way. Like it's not like I probably won't remember any of it, but I can try.
Yeah. So we're just looking at using some real life examples. So this was a real one to figure out the grading of the property. And then like there are some other views. Where is it? This one, like this one here. I needed to calculate the stair stringer. And we had the formula, right? We were using Pythagorean theorem.
Yeah.
We just had the incorrect measurements.
Well, yeah. You were measuring from the bottom of the plank to this thing, so you were off like a couple feet.
Yeah, I was off by a couple feet. Yep.
That's what happened to me and my dad, though. We were building a garden for my mom. We had to drill in these posts into the ground, and we had to measure them, but it was really hard to get them to be level and straight. So we had to, we live out in the country, so we usually don't use math, but we used a little bit this time.
Yeah. So for this example here, just because Pythagorean theorem is one of the skills that we're working on, and I'm also going to do a little bit of mental math here, but so we knew this measurement now, and in my mistake, I used the this 8.5 measurement instead. But now that we know this measurement, and I actually have enough information to figure out this measurement because it takes a little bit of mental math to think about. So my dad had these boards, so the key is that he knew the boards he wanted to use, and the key is that we know the height. And so we have to figure out how many stairs to put in.
And that's like what, 20 stairs?
Well, see, we needed to figure that out because you also need to know how many stair boards to buy. And so what we did, if you are, again, I wish I could show my phone or something, but essentially the way stairs run is you have one like this, right? Okay, something like that. Awful drawing, I understand. But this board here would be one board, and then this would be another board, and they don't overlap. Like we have the stairs so there's no overlap. So if I can figure out how many stairs fit that space of the 10.5 feet, then I can figure out how many boards I need. So the first thing I needed to do is figure out the number of stairs. And my grade 10 class was really awesome with that. They said, okay, well, we're going to take the 10.25 height and we're going to divide it by the height of a stair. But this was like, this is where we ran into some problems because this is in feet and the height of stair, if you recall, needed to be between 6.5 and 7.5. And ideally you wanted 7 inches.
So then you have to convert inches to feet?
You had to convert the feet to inches. So they did this work for me. They took the 10 and multiplied it by 12. And then 0.25 of a foot is 3 inches. So then they added 3 inches to it. So this 125 feet is actually 123 inches.
So
and that's
what, 23 stairs?
Well, so then we took the number of stairs equals the 123 inches of height divided by, we tried 7 first. And that gave us 17.57 stairs. But we were like, we can't have 0.57 of a stair. So the class said, well, it doesn't have to be exactly 7 inches. So they said, what if it was just a little bit lower? Because we decided that having just a shorter stair would be better than having just a little bit higher stair. So they started to play around and they tried 6.5.
That probably wouldn't work because it would probably do the same thing that the 7 did.
Yeah, so then we were at 18.92 and they were like, that's not right. So then they tried another one. And they did
a whole number, I assume?
No, they tried 6.8 next, I think. And that gave them 18.09, which to us was like, that's close enough. So this is about 18 stairs.
I figured I can, yeah.
So that was one option. But then we were like, well, what exactly should it be to fit perfectly? So if we wanted 18 stairs, but we wanted to get rid of this 0.09, and this is just an extension. So just to show you what their mathematical thinking was, which is pretty cool. They said, if I know I want 18 stairs, then I need to take the height and divide it by some number. I don't know this number, right? I don't know exactly the height of the stair that I want. So I'm going to make that my variable and solve for it. So how do I do this when my variable is on the bottom? And that's one of the solving skills that we're working on.
I'd say take the 123 and divide it by 18. But I feel like that's what everyone would do initially, so that probably isn't right.
Well, it actually mathematically works out that you do just end up swapping these two values.
Oh, okay.
Yeah. Honestly, I can do the long way or I can do the short way. And the short way is that if your variable's on the bottom, then you can just switch it with the one that's over here. So it does end up being 123 divided by 18, which then the height of each stair would be 6.83 continued inches.
Okay.
So, and that works out to like this really cool fraction, but I don't want to like go off on this tangent, but it'll actually give you a perfect fraction. Like, it's not 15/16. It is 7/8, not 7/8. Anyways, I'm not going to get too distracted. So anyways, they went through this process and they were like, okay, so each stair is going to be just a little bit bigger than 6.8 inches. Like that's how high each stair is going to be. And they wanted to just figure this out so that they like knew exactly where we were going to put these measurements on the stairs. So if my dad needed to, oh, I've colored it all up now. Let's see, do I have another one? Yeah. So my dad needed to like bore out the holes to put the stairs in. So he knew he needed to put them in 6.83 inches up this way here.
Yeah.
Okay, so that's one application. So in this, we have done a little bit of mental math. We have done some conversion from feet to inches, and we've actually done a solving skill, which is another practice.
That's a lot of math.
That's a lot of math. So then the other part of this is, let's have a look at that stair again. So if I have stairs that are like this, and they never overlap, right? Mm-hmm. Then that first stair is going to take up this amount of space. And that second stair is going to take up this amount of space, and that third stair, and so on and so forth, that each stair is taking up some space on the bottom until we get to the end. And in our case, if we have 18 stairs, and let me just go back here. The information my dad gave me is that each of those boards are going to be 9.5 inches wide. So this stair board this way, or the stair board, let me get a better view. The stair board against this, across this way, is going to be 9.5 inches. So to figure out what this length here on the bottom is, like how am I going to figure out this piece here? I would just take the number of stairs and times it by how wide each stair is going to be.
But that number is the wrong amount of stairs, I am assuming?
No, it is the right one. We're using the right calculation. I used the wrong height before.
Oh, okay.
Yeah, so I was a stair short, so I actually had 17 stairs in my calculation. So this is 171 inches, which if we do a little bit of mental math, 171 divided by 12 gives me 14 feet, 14.25 feet. So the measurement, we know this one. What color did I do? Green? Sure, let's do it in green. We know this height because we measured it, and we now figured out this one here.
So you figure out the amount of length you need for the siding. Then you just need to figure out how many stairs you need to put on.
Yeah. So we figured out we need 18 stairs, and we figured out, we measured this height. So that height was 10.25. feet.
You've just bought the ones, like the side for the stairs, and then figured out how many stairs you would need?
Well, yes, that's one way to do it, but then we would have had to cut each of the width of these boards. And like I said, that's actually a very tricky thing to do because you would be cutting along this edge, and that requires a very big saw, which my dad does have. But we just wanted the simplicity of using just the size of the board as opposed to cutting
Yeah,
it down.
yeah, that makes sense.
Yeah, because the more you adjust the more you adjust this angle of the triangle, like if you were to pull this back to
Then
make the run shorter, then your stairs still need to be the 7 inches high. So then it would influence kind of how you put the stairs in here, and the boards would have to be changed to fit the piece of wood. So we wanted to fit the wood to the stair length that we had.
yeah.
Okay, so we had this height here now that we've measured it, and we figured out the run. So this is our run, and this is our rise. Oh, I could have just used the pen that's in my hand. I love how I'm using my mouse and I use the pen that's in my hand. So now that we have that, I can actually use Pythagorean theorem to find the length of board here that we would need.
Oh,
So,
okay. That makes more sense than what I was gonna do.
well, listen, it made more sense than what I actually ended up doing.
I would have measured like the width of those two poles together, and then just like, I'm like, okay, I need to do this, and then.
Mm-hmm. So, and then he actually asked me another question, which we will figure out because it's another application of trig, but it's again finding another angle. But okay, so he gave me this. We have this information now. I've got 10.25 here, and I've got 14.25 here. At no point in time did I say a 3. I don't know why I wrote a 3.
Probably didn't mean to.
And then I need to figure out this one here, which is the hypotenuse. And so Pythagorean theorem tells me that this long side here, h or c in our formula, right? We have a squared plus b squared equals c squared. In grading, they use rise squared plus run squared equals, they do use the h. But it's essentially saying the exact same thing. And someone asked me this yesterday. They were like, why, where do the X and Y come from? And I said, well, they just simplify it. So rather than writing out rise and run all the time, rise and run, I can change it with a letter just to make it easier for me to see it.
Just turn it into a variable.
Yeah, so you just turn it into a variable. So that's where that comes from. So I can actually just input my calculations that I have. So my rise, according to this one, is 10.25, and I square it. And my run is 14.25, and I square that. And that will give me the length of the stair stringer squared.
Oh, okay.
So I'm just going to put that into my calculator. I guess I could do that here if you wanted to see it. Okay, so I take 10.25. That's not the right number. And I square it.
Yep.
That gives me 105.
Squared numbers together.
Yep. 0.0625. And then I need to take my 14.25 and square it. And that gives me 203.0625. And that, I ran out of room, but it equals the length there. So I take those two numbers and I add them together. So I have 105.0625, and I'm adding it to the 203. $308,125. Okay, so that gives me this number. So how do I then change it from a squared to find out what just h is? Because right now I have h squared.
Maybe you divide it by itself or divide it by the top number.
Well, what's the opposite of squared?
Multiply?
Not quite.
I don't really remember. Like,
that's okay. That's okay. This is just this is all learning and all bringing it back. That's the whole point of this. So h squared actually just means h times h. So we're trying to find what number multiplied by itself gives us 308, and the opposite of h squared is actually the square root.
oh, okay. I remember that now.
Yeah, and math really likes to go forwards and backwards all the time. So we always have a complementary operation. So if we're squaring something to go backwards, we would take the square root. If we're multiplying something to go backwards, we would divide. Everything's got this opposite. We can take the tan, or we can take the opposite, which is the tan inverse. Like everything in math has a complementary partner, which does the opposite for it. So I'm actually just going to tell my calculator, and this is where the benefit of your phone calculator or your computer calculator comes in, because on my handheld calculator, I have to put in square root and then the number.
Right.
But here, the number is already up, and I can actually just go, take the square root of that, please. Because in this calculator, I put the number and then tell it the operation.
It's just programmed better.
It's programmed differently, and it depends on what you're using. Like if you go further in math, I personally prefer the handheld calculator because of the more challenging concepts that I do. It just makes it easier later on. But for doing these, why not?
Yeah.
Okay, so we got this number, 17.55 something or other. This is feet. And so that just means that that's the size of the board that I need to buy. So I told my dad, buy an 18-foot board. From here to here. And what messed up is when we did it with the wrong height calculation, that board was short.
Oh, it was short like a couple inches because of the miscalculation.
Yeah, it was short a whole extra stair here. So anyways, and yeah, it was a kind of a whole learning experience. So the board ended here, and we needed it to end further down. So we actually missed this whole height of this extra stair here on the bottom. But anyways, learning experience, we all get it. So the ultimate goal is I told my dad to buy an 18-foot, or he needs to buy an 18-foot board.
But it should have been a 20?
No, it was a 16 and it should have been an 18.
Oh, okay, that's quite a bit of a difference.
Yeah.
That's like 3. Yeah.
Yeah. So then my dad extended it further and said, okay, now that we have this board, I need to know what angle do I notch in the wood to slide my stair in, because he likes to do, I know I'm going to get it wrong, but it's like tongue and groove. So like you notch the wood and slide the board into it as opposed to just like kind of nail the board or screw the board in from the outside.
That's
So
it.
we wanted to set up his machine. So we actually wanted to know what the angle was. So we actually had to go further and calculate what this angle here was.
Oh, I think that's what
Yeah,
we do.
there's a whole lot of math in this problem.
Probably took a
And
long
if I'm
time.
being like honest with everyone, my dad didn't finish high school, and that's probably one of the biggest things he regrets in his life. Um, so for him, he needed me to come help him do this math problem so he could build his shop. And he's so capable. So it just kind of blows my mind that he would need my help, you know?
Well, math is annoying for like a lot of. He probably doesn't like math.
He actually really does like math. He just didn't like school.
School
In the
does suck.
Yeah.
Well,
And it was different then too than it is now. So,
a lot
uh,
more bullying and stuff happened.
well, I think the same amount of bullying happened. It was different. Like I think he was expected to go to work and, um,
Yeah,
he
he
went out and got a
got to get a
job
job
instead of,
at like 16 and then provide for the family already.
Mhm,
And he feels comfortable doing that because you've got the freedom.
mhm. So one of the other things he asked me is what angle do I need to, if you break down each stair here, he needed to know what angle to do this stair at. Um, and so we actually are able to find that as well. So again, this is going to be using our Sokotoa.
Oh, Sokotoa. Oops.
And because I want to show a different formula rather than the tan, because we'll just keep using tan over and over and over again.
That's the
Um,
most common one.
Yeah. I know that each stair is going to be 9.5. Oh, no, we're not going to do it that way because I'm right back to TOA.
Can't avoid it.
Well, I can get there. I can get there. Okay, so if I know this measurement here, I'm just picking one, and I actually know what the length of that hypotenuse is because we just solved for it, 17.55. I can put that in as well. So step number 1, it's writing in, black. Write in black, please. Step number 1 is to label. So I go to the angle and I need to label this side as the opposite. The one across from the 90 is the hypotenuse. And the one down here is the adjacent. Okay. And then step 2 is pick a formula. So which formula do I use?
Well, normally you'd use TOA, but you could probably use opposite. You could probably use SOA.
So SOA requires me to have the opposite and the hypotenuse. In this, what I've drawn here, do I have the opposite?
Wait, yes. I think you
Not
do.
in this drawing.
Oh, no. Sorry. I just thought you meant like the letters. No, you don't.
So what sides do I have?
You have opposite and adjacent.
I don't have the opposite right now.
Or sorry, you have adjacent and hypotenuse. So you would use
Hypot.
ka.
So I would use ka, right? So we're always working off it. Now, technically, I do know the opposite measurement, but I wanted to like drive home what to do if you didn't have all of the measurements. Okay, so I'm going to use ka because I have the adjacent and the hypotenuse. So then I'm just going to write the formula. And again, I need to make sure that I put in that theta or angle measurement.
The variable, yep.
The variable. And here we go. There's my formula.
Okay.
My next step is to sub in the values. So I don't know what cosine is. I don't know why I put an S. Sorry. I don't know what cosine of the angle is, but I do know what my adjacent is. If I go up here, my adjacent is 14.25. So I can sub that in.
Instead of hypotenuse?
Instead of adjacent.
Oh.
So wherever adjacent is, I put the 14.25. And wherever our hypotenuse is, I put the 17.55.
So would you divide those two numbers by each other?
Yes, you would. So I still don't know what cosine theta is, but I have a calculator and I can put 14. I'll show you what I'm putting in my calculator. I will put 14.25 and I will divide it by 17.25. And that will give me, that's not right. It didn't put the decimals in. Let me try that again.
813 seems like a lot.
Yeah, that was way too much. There's your mental math, knowing when you have the wrong answer. 14.25 divided by 17.25 gives me, that's a better number, 0.826, so 83. Last time I used 5 decimal places. This time I chose to use 2 decimal places. Honestly, use whatever works. And we're going to get kind of, again, that kind of range of answers. If I use 0.8, I'm going to get one answer. If I use 0.83, I'm going to get another answer. If I use 0.826, I'm going to get another answer. And that continues, but we want just like kind of an average of the answers.
Yeah.
A range, as long as it's close. Okay, so this is what I have. How do I get rid of cos?
How do you get rid of cos?
I want theta by itself. I want the angle variable by itself.
Well, you can do a few things, I think. But what I would do is I would just take cos and divide it by itself.
Yes. So I'm going to take cos. Oh, I didn't want to do it in that color. Sorry. My computer is just being a little bit slow.
Is it?
Yeah, see, blue is selected, but it's taking its time and actually picking up the blue color.
When did you get the computer?
Honestly, it's not the computer. I know it's just me.
Oh.
There, see, blue. What is your problem? Blue. Save me, save me. Okay, well, we'll just go with what we have. So I divide both sides by cos. Okay, and that cancels this cos and leaves my theta by itself. But then I don't know how to deal with this 0.83 divided by cos.
Well, it would technically turn into cos, but then you said before that it went into minus version. So,
yeah. So to bring the cos from the bottom up to the top, it turns into the -1 version, which is the inverse or the opposite. And we would get something like that. And then my lovely little calculator. Computer and phone calculators will make you put the number in first. So I put in 0.083. Then I go to my trig and I tell it I want the second cosine. So I get that negative exponent.
Right.
And that tells me that this angle
was 33.901.
33.901. So when my dad set up his machine, well, actually, he used a square. Let's see, where's the picture? Picture's all the way back up here. We took that 18-foot board and we measured 33.9 degrees. And then we went up the 6.8. If you recall, where did we find the 6.8? The height of the stairs, 6.8. We went up 6.8 and we measured at another 3.9 degrees. And then we went up another 6.8 and measured at a 33.9 degrees and went up another 6.8. And so that these stairs were all ready. They were all marked off that we just cut the board and put them on.
Oh, okay.
And that was just what it took to build the stairs of a balcony.
I would have died.
But in this problem, we have done so much math that we've done a lot of review of course contents that we need to kind of have or need to at least see so we can kind of recognize when they're happening throughout this course. So we talked a little bit about the slope, which is the rise over the run, which in landscaping is called grading. We actually calculated the difference in the rise based on two measurements, right? Then we went on to use that to solve for an angle. Because we had two sides of a triangle, we could use the trig ratios to solve for it. So we found the slope of the land to be 16.3 degrees at that point. Then we went on to talk about figuring out the length of this board. And we had to do some mental math, and we actually had to use some solving skills, and we actually used some trial and error. Never discount trial and error. It's a great system sometimes to help us get to a point. And if you go on and take grade 12 college math, you actually have to use trial and error. There's no other way for you to figure something out, for you to figure out the exponent work without trial and error, because we don't teach you log. Then we use some more mental math with some visuals to talk about how we figure out the run across these part of the stairs. Then we also went and did some more Pythagorean theorem. We used squares and we used square roots. And then we actually turned around and made our answer make sense. So you don't go to the shop, you don't go to the hardware store and say, I need a board that's 17.55 inches. They'll say, here's an 18-foot board.
Yeah, then you have to cut it.
Then you have to cut it, right? So we needed to know that we couldn't order a 17-foot board. We needed to know that we needed to go bigger, right, for that board.
Yeah.
Then we tried trig again. And we kind of worked on a little bit of stuff that'll set us up for some exponent rules tomorrow with the negative exponent, with cosine. But that's a lot of math.
It's a lot to take in, that's for sure.
Mm-hmm. So I hope that was helpful. I know it was a little bit longer, but for me, I'm just going to stop the recording in a second. So for me, The whole goal is that we just get a little bit more comfortable with math in this crazy quadmester that we have going on and this crazy pandemic and some people finishing grade 10 and some people not finishing their grade 10 math. We can only do what we can do. And so one of the reasons why I've designed the spiral is that we're going to touch on each topic a little bit. And then when we're done that, we're going to go back and touch on each topic a little bit more. So we're going to build on the skills, but that gives us some time to think about it. So I'm not going to hop right into the next trig part. We're going to take some time to think about this trig part first.
And are we doing a project with this one?
Yep.
Right. When is that due?
Oh yeah, not quite yet. We're working towards it. It'll be the next week. We'll start working on some consolidation work.
So all I have to do right now is the assignment I was working on this morning.
Yeah, the refresh task, and that's so that we can practice some of these skills like, now I can't find it, like slope, like Pythagorean theorem, like this solving that we did here, rearranging or balancing of equations. What else did we do?
Oh, we did all.
We did a lot. We did a lot. Substitution, so where we sub in a value, like all of that's really good stuff, but that's what we're going to be practicing with the refresh task.
Perfect. Yeah, that'll be good.
All right, so I'm just going to end my recording.